Welcome back, everybody. Today we're going to continue talking about our own galaxy, the Milky Way, and also we're going to start talking about other island universes. So previously, as a summary of what we covered last time, we found out that the shape of the Milky Way on the night sky shows us that we live inside of a flattened collection of stars in a disk shape. We found that it's pretty hard to count stars or see stars in the plane of the disk because of dust extinction. There's a lot of dust in the disk of our galaxy, and that dust tends to absorb visible photons of light. And so things behind a dust cloud get fainter and also redder. The other thing we discussed is just how hard it is to measure distances to stars. Stars are very far away, and if we want to try to measure their distances through stellar parallax, through that apparent motion of stars on the sky, it's a very challenging measurement to make. We talked about a few satellites, Hipparchus, that was launched in the 90s and measured distances to hundreds of thousands of stars, and Gaia, the brand new satellite that's going to start operating in a month or so, that's going to be able to measure parallaxes for stars across almost half of the galaxy. So that's an exciting development to watch out for. Beyond a few thousand light years at the moment, parallaxes are too small to measure with current technology, so we need another method. And we talked about what astronomers use instead. Astronomers like to use objects called standard candles. We call these standard candles because for these objects we know, or we can deduce, what their intrinsic luminosity is. Now, you guys know by now that if you know what the intrinsic luminosity is, then you can estimate what their distance is by measuring how bright they appear to be on the sky. So if we know L and B, we can solve for D in the inverse square law relation. What do we use as standard candles? Well, some stars at the end of their life show periodic brightness variations, and these brightness variations are correlated with how luminous they are. So by measuring the period of these variations, you can deduce how luminous the star must be, so that then by measuring their apparent brightness, you can deduce their distance. And so these stars can be used as standard candles. We found that globular clusters have many of these standard candle stars, these variable stars, and so are also great distance indicators because they're not confined to the disk of the galaxy, and so they don't suffer as much from dust extinction. By measuring distances to globular clusters, we can estimate the diameter of the galaxy, and we see that it's close to 100,000 light years, and that our solar system lives within the disk about halfway out. Not near the center, not all the way at the edge, somewhere in the middle, nowhere in particular, about 30,000 light years from the center of the galaxy along one of the spiral arms. So here's our current model of the Milky Way. This is a face-on view. We're looking down onto our galaxy if we were able to travel away from it. And the sun is at the center of this coordinate system over here towards the south to under the bulge. And you see that the disk has a sort of bright center, which we call the bulge, where there's a lot of stars. And coming out of that bulge are these long spiral arms. The sun is located along one of these spiral arms, somewhere sort of halfway out. So here's that disk. Here are the spiral arms, and that's where we are. That's the bulge at the center of the galaxy. And the whole thing is about 100,000 light years across as we measured from those globular cluster distances. So if it's so hard to see through the disk because of all of that dust, then how do we know that our galaxy has spiral arms and also a bulge at the center? I mean, if it's so hard to see into the disk, then how do we know for sure that our galaxy looks like this when seen from the outside? The answer there lies in the fact that the dust is opaque mostly for visible light. So to our eyes, the dust is really a problem for observations. But if we use other wavelengths that our eyes can't see but that our telescopes and cameras can, then we can sort of go around that problem. So this is a picture of galaxy in visible light, so what the galaxy looks like to our eyes. But this is what it looks like in the infrared. So that dust that has been absorbing those visible light photons tends to re-radiate those photons in infrared. So you see the dust glowing brightly in the infrared. We can also look at the galaxy in radio wavelengths. So really using a multi-wavelength view, that's the terminology that astronomers use for when we look at something from many different wavelength scales, so infrared, radio, microwave, X-rays. That gives us a multi-wavelength view of an object, which generally gives us more information than just using one wavelength, like, visible light, or one wavelength is like red light. So what does looking at the galaxy in the radio tell us, for example? Well, radio emission comes mostly from hydrogen, from neutral hydrogen atoms, so atoms of hydrogen that have one proton and one electron. Hydrogen atoms can emit light at a very specific wavelength. That wavelength is 21 centimeters long, and they emit that light during a spin-flip transition. Now, this is sort of a complicated quantum mechanics effect, but you can understand it fairly easily by knowing that protons and electrons have a certain spin, a certain direction of rotation, if you will. And that when the proton and the electron in the nucleus are aligned with each other, so they're both pointing in the same direction, that's a higher energy configuration than when the proton and the electron are pointing in opposite directions. And quantum mechanics tells us that it's either one or the other. They can't be at any sort of intermediate angle. They're either parallel or anti-parallel, parallel or opposite. And when they flip from one orientation to another, when the electron flips around, then because you're going from a higher energy state to a lower energy state, a photon is emitted. So energy is released in the form of light, of a photon. So if that wavelength emitted is 21 centimeters long, what does this say about the difference in energy between these two states? Remember, the wavelength of visible light is between 400 and 700 nanometers long, whereas this wavelength is 21 centimeters long. So 21 centimeters is a very, very long wavelength. It's about the wavelength, the distance from wavefront, from peak to peak, is about the distance between your thumb and your pinky outstretched. So that's a really long wavelength. Now, you guys know that for a photon, the wavelength and the energy are inversely related, right? So the wavelength, the longer the wavelength is, the smaller the energy of the photon. So this is a very, very long wavelength, so the energy is very, very small. It's a very small amount of energy, which tells you that the energy difference between these two states, between parallel and anti-parallel, must be very small. These spin-flip transitions, they don't happen very often. They happen very rarely, in fact. Once, in order for them to happen, you start from one of these lower energy configurations, and these collisions between atoms, which happen very rarely because this material is very diffuse, so atoms aren't really crashing into each other like they are at the cores of stars, for example. These are really cold, diffuse molecular atomic clouds, and so collisions really don't happen very often. But once they do, this electron and proton system might transition to the higher energy configuration of having their two spins aligned. And once the atom reaches this higher energy level, then it sort of automatically decays to the lower energy level. But the time it takes to decay from one level to the other is on the order of millions of years. So these transitions happen really very rarely because the collisions happen rarely, and then it takes a long time for the atom to decay from the higher energy configuration to the lower energy configuration. But fortunately, there's a whole lot of hydrogen out there. There's a lot of hydrogen in our galaxy. So we actually see these photons being emitted all the time. And because they have a wavelength of 21 centimeter, that's in the radio wavelength regime. And so we use radio telescopes to measure these wavelengths. Interestingly, these spin flip transitions is sort of the same physics that's behind MRI scans. If you've ever had to have a magnetic resonance imaging scan, this is the type of physics that was being used in order to image the different tissues in your brain or in your knee or whatever you imaged. So by knowing that atomic hydrogen emits this wavelength at this very specific transition, we can now look through the galaxy and look at Doppler shifts in that 21 centimeter line. So sometimes we might see 21.01 centimeters, and sometimes we might see 20.99 centimeters. So we might measure a small shift with respect to that 21 centimeter rest wavelength, and that tells us whether those clouds of hydrogen are moving towards us or away from us. So if the clouds of hydrogen are concentrated mostly along those spiral arms, then by looking through the galaxy and finding these little shifts, you can figure out where those spiral arms are and whether they're moving towards us or away from us. So in this picture here, our solar system is symbolized by the letter S for our sun. And if we're looking at clouds in position 1, 2, 3, and 4 along those spiral arms, then which cloud, 1, 2, 3, or 4, do you think we will measure the largest shift for? So, an opportunity for you to check your understanding. Which cloud of gas, 1, 2, 3, or 4, will show the greatest shift in the 21 centimeter line? And will it be blue shifted or red shifted? So both 1, 2, 3, and 4, all of those clouds are actually moving towards us because the galaxy is spinning around the center, and all those, you can see from the velocity arrows for each of those clouds, they're all moving more or less toward the sun. But cloud number 2 is the one that's moving most directly at the sun, and so that's the one for which we'll measure the biggest shift. So that's the one that has the greatest velocity in the direction of the sun. And of course, that shift is going to be towards the blue side of the spectrum, so it's going to be a blue shift because the cloud is moving towards us, and so the wavelengths emitted are getting shorter. So this is the technique with which we measure and determine where the spiral arms are in our galaxy. And this is a picture taken with one of these radio telescopes, a map of what the galaxy looks like in neutral hydrogen. So using this spin flip transition, and where at the you are here dot, and that's the center of galaxy, and this is the location of all of those spiral arms. So this is actual data from these hydrogen clouds. So what about, we've looked at what the galaxy looks like in visible, in infrared, and radio. What about when we move to higher, more energetic frequencies? What does the galaxy look like in X-rays? So once you move to X-rays, there's going to be less stuff emitting X-rays, right? Because X-rays require really energetic processes because X-ray photons have a lot of energy. So the things that are emitting most of the X-ray photons are really energetic objects like white dwarfs and neutron stars and black holes, these stellar remnants that are extremely high temperatures, or in the case of stellar remnants of black holes, they're accelerating things next to them to such high speeds that those things start emitting X-ray radiation. So most of the things you see here, most of those bright white or yellow dots are actually stellar remnants, neutron stars and black holes. So that's pretty cool. So we can see all of these crazy objects in the galaxy. But you see that there's more of them towards the center of the galaxy, and that's partly because there's just more stars there overall. It's a lot denser in the center than it is in the outskirts, but also because things get really energetic at the center of the galaxy. So this is a zoom in towards the center of our galaxy, again in X-rays, and this is about 900 light years across. And remember that the galaxy is 100,000 light years across, so this is about 1/100th of the size of the galaxy, so we're really zooming in. And this is in false color, of course, because our eyes can't see X-rays. So this is an image taken by the Chandra Space Telescope, and it is showing you shorter and longer wavelength X-rays. They're all X-rays, but the shorter wavelength X-rays are in blue, and the longer wavelength X-rays are in red. And the intermediate ones, I guess, will be in white. So you can see here that there's all these little tiny sources of X-rays, and those are all sort of stellar size emitters, so again, stellar remnants. But then in the very center, there's this sort of faint glow in X-rays. That corresponds to very hot gas at the very center of the galaxy that's emitting these X-ray photons because it's heated up to 100 million degrees Kelvin. If you zoom even further in, and this time we're actually looking in the radio again, we can see the very center of the galaxy. There's all these really energetic processes going on. So you see these filaments of very hot gas being excited around the center of the galaxy. These filaments follow sort of magnetic field lines around the very center of the galaxy. And if we zoom in again further, you start looking at this mysterious object, Sagittarius A star, and that is where we believe resides a very large supermassive black hole. That supermassive black hole is affecting everything around it and causing these very energetic processes to happen. So how do we know that there's a supermassive black hole at the center of the galaxy and not just some other very massive object? The most direct evidence we have of the supermassive black hole is by looking at the orbits of stars that are located very near the black hole and are orbiting around it. So this is an amazing piece of research that took over 10 years to do. Astronomers have been photographing the very center of the galaxy since 1992 in infrared light. So infrared light is not as absorbed by dust, and so you can use it to look, and stars in general tend to emit a lot of infrared light, especially low mass stars like K and M stars tend to, their peak, as you know, since they're cooler, their peak is in the infrared part of the spectrum. And so we can use infrared telescopes to look at stars near the center of the galactic center without suffering so much from dust extinction. And So astronomers have been looking and taking pictures of the center since 1992. And now that we have all of this data over all of these years, we can actually make a movie of what these stellar orbits look like by essentially following the motion of these stars in the galactic center. So here we go. The location of the cross here is where we think the black hole has to be. And so you can see, especially for this star, look at how, first it's a very elliptical orbit. It comes in and it makes this very, very elliptical orbit right around one focal point. And there must be some mass at that focal point, right? Through Kepler's laws, this star is orbiting in an ellipse around some mass, but we can't see anything there. There's nothing there emitting light. And that's how we deduce that there must be a black hole at that position. You can deduce how massive the black hole has to be by just how fast the star is going around the black hole. This is another group making very similar measurements. These ones have taken a little bit longer to make, but you can again see, I like this representation because you see the stars, but then you also see the orbital paths that they are traveling on. And so you can see each star appears to be orbiting around that central point where that star is located, but there's nothing there. We can't see any light being emitted from it, even though all of these separate star orbits are obviously orbiting around a focal point that is at that location. Again, these are real observations of individual stars orbiting around the supermassive black hole at the center of our galaxy. So the center of the galaxy is very crowded. There's about 10 million stars per cubic parsec at the center, versus 0.2 stars per cubic parsec in the solar neighborhood. So very, very crowded. I like to think about what it would be like if we were, the Earth was orbiting the Sun, but the Sun was actually near the galactic center rather than out here in the outskirts. If we were in that crowded region of the galaxy, there would be 1 million stars in the night sky that would be brighter than Sirius. So this whole sky would be lit up with millions of stars brighter than Sirius, the brightest star in the sky. So here's another view of our current model of the Milky Way, this time edge-on. So we see the very thin disk. We see that the Sun is located about halfway out, so a little bit over halfway out, 30,000 light years from the center. We see the bulge at the center of the galaxy. Obviously, we don't see the supermassive black hole because it's obscured by the dust, and it's also extremely small on this scale. But we also see, we see the thickness of the disk. And notice that the disk is only 1,000 light years thick, but it's 100,000 light years wide. So the aspect ratio of thickness to width is 1 to 100, which is about the same as a CD or a DVD. I know that you have in your mind how thin those things are, so it's really quite striking just how thin galactic disks are and how they are able to stay in this very thin configuration for so many years. That's in fact a little bit mysterious for astronomers still today, is how they can survive in this very thin state when so many things are happening to them over their lifetime. So you can also see in this picture the globular clusters. Those are those little smudges that are sort of surrounding the galaxy in all directions. So those globular clusters are distributed somewhat symmetrically and spherically around the galaxy. They're not confined to the disk of the galaxy. And that's again why we were able to use them so successfully to measure distances over such a large scale, because they don't suffer from as much dust extinction as things that are found within the disk. The disk is embedded in this large spherical halo where the globular clusters live. There are also stars in that halo. This is a picture of the Sombrero Galaxy, so this is another galaxy, not our own. But this is a picture from the Hubble Space Telescope, and you can see the very thin disk that is inserted into this sort of spherical distribution of light as it appears to us here. This light is actually caused by many, many, many stars. They're too small to resolve in this picture. And again, in this halo, you also see the globular clusters, which are again too small to see for this particular picture. But most of the gas and dust in a galaxy is confined to the disk. There's really not much cold gas or dust outside of the disk of the galaxy. So another check here. So the stellar population in the disk must be older or younger, bluer or redder, more or less massive than the population in the halo, on average. So I just told you that all of the gas and dust are located in the disk. So then what does that mean for the population of stars that you see in the disk versus the halo? The key to answering this question is, of course, that because there is no gas or dust in the halo, there is no star formation going on right now, because there's no gas to form new stars. So the only place in the galaxy that has gas that is capable of forming new stars is the disk. And that means that the stars that exist in the disk are on average much younger than the stars in the halo, because they're still being formed as we speak, whereas the halo stars are all older because there hasn't been any new star formation in the halo for a long time because there's no gas. Cold gas, sorry. The stars in the disk are, because they are younger, they're also going to be bluer, hotter, etc. Because, again, because you're seeing stars that have recently been born, some of those stars might be the big, massive stars that live for a short period. We're still seeing those because star formation is currently occurring. For a population where stars have not been formed in billions of years, then you won't be able to see any big, massive blue stars, because those will have already died off since the last episode of star formation. So recent star formation is confined to the disk, so stars in the disk are, on average, younger, bigger, and bluer than stars in the halo. That means that there are no young massive stars in the halo of the galaxy. So why are galaxies, or at least galaxies like our Milky Way and the Sombrero Galaxy, why do they have these thin disks in them? The disks of galaxies form, once again, as we've seen in other parts of this course, these disks are formed due to angular momentum conservation. So galaxies were not always there. They're not eternal objects. They too were formed at some point. And galaxies generally form through gravitational collapse in the very early universe. So small bits of matter will attract other small bits of matter, and things just start collapsing inward. So you go from something that's big and extended to something that's smaller. And again, when the radius decreases, so when things collapse and contract, their rotation speed goes up. Again, just like the ice skater bringing in their arms and spinning faster. So when things collapse, they pick up rotational speed, and that rotational speed is then going to flatten out the distribution of matter into this disk, much like the pizza dough analogy, where you spin the pizza dough around in order to make it flatter. So here's a video of a simulation made in a supercomputer. You need a lot of computing power to do these things, but it's a fairly realistic simulation of what we think happens when galaxies form. So you'll see that this galaxy keeps on piling more matter on top of it so that it grows, and things sort of fall into the galaxy from outside. And as they fall in, they just add to that rotational speed. It's sort of a very violent process. There's a lot of collisions going on because things come in lumps. We'll learn more about that later. But as things come in, they get added to the disk that grows bigger and bigger and bigger. You start to see also that the center is a little bit more dense than the outskirts. So you can see the formation of the bulge there at the center of the galaxy. Sometimes when things fall in, spiral arms become more pronounced. Sometimes they become less pronounced. So this is obviously a very accelerated movie. Each second corresponds to millions of years. Right now you see a bar formed at the center of the galaxy, and as we'll find out later in the course, we see these bars in many spiral galaxies in the universe. It's still under debate, actually, whether our own galaxy has a bar like this or not. Because, like we said, it's pretty hard to measure things when you're inside the galaxy, so it's hard to measure exactly what the galaxy looks like from the inside. When we look at other galaxies in the universe, though, some of these galaxies have these very pronounced bars that are sort of rotating, spinning at the very center of the galaxy. That's our galaxy. And now I want to talk about the second part of this class, which is the island universes. So, for a long time, astronomers didn't know whether the galaxy, as we saw it, was all there was. They didn't know if the galaxy was the same thing as the entire universe. They didn't know if there was anything outside of the galaxy, because remember, the farthest things that they could measure were sort of using these variable stars, and they couldn't go very far out. So we couldn't really measure distances to things that were further than these globular clusters. But even in the 1700s, astronomers were observing the skies and noticing that there were a lot of little fuzzy patches of light in the sky. We call these nebula, and nebula is the Latin word for cloud. So these were little clouds of light in the skies. And the person who first made a catalog showing all of these big and bright nebula in the sky, his name was Messier, and he was actually the French royal court astronomer. Back in those days, kings were quite superstitious, and they believed that comets were bad omens. So they didn't want to take any big decisions without knowing if there were comets in the sky. So they actually hired Messier to look for comets constantly and to advise the king on, whether he should invade Great Britain or not. So that was Messier's job. He was a comet finder. And he found that as he was looking for comets, he kept finding these fuzzy, patchy things in the sky that looked like comets, but were not in fact comets. And so he would find these things and get really excited, and he would say, "Oh, there's a comet," and then he would follow it for a while and realize that it wasn't moving in the sky, and realize that no, it was not a comet. So he got really frustrated because he kept finding the same clouds, fuzzy things that weren't comets, over and over again, and getting excited, and then realizing that he'd seen this one before and that it too was not a comet. So he made a catalog. It's now called the Messier catalog, and essentially it's a collection of objects that are fuzzy but are not comets. So that's what joins all of these objects together. That's the common theme. And so all of these things, all of these objects in the sky looked like fuzzy patches of sky back in the 1700s with, telescopes that weren't very good. And some of them looked slightly different than others, but it wasn't clear what their nature was. These days, we can take much better pictures with our bigger telescopes and better cameras of what these things look like. And so we can see that these are all very different types of objects. So you might recognize, especially along the left-hand side, there's a lot of globular clusters, so very dense collections of stars. But there are also things like this guy here, that's a star formation nebula, so that's a cloud of gas and dust that's forming stars as we speak. On the other hand, something that looks like this is a picture of the Ring Nebula, again a cloud, but this is a planetary nebula. Again, the name planetary nebula doesn't make any sense. They're called planetary nebula for historical reasons because at the time they sort of looked like planets, through those telescopes that didn't work as well. Now we know planetary nebula to be the dying shells of a dying star. So the star in the center is a white dwarf, and as that star collapsed, it shed its outer layers through periods of mass ejection, as we talked about before in class. So that's the Ring Nebula. This one down here is the Orion Nebula. This is a place, again, with where stars are forming from big clouds of gas. So all of these things are located within our galaxy. These are clouds of gas forming stars or dying stars in our galaxy. But some of these objects don't quite look like the others. So this here is the first recorded sketch of M51 through a telescope. This was done by Lord Rosse in 1845. And he really captured the spiral arms of this nebula very clearly. And his opinion was that these types of nebula with these spiral arms look nothing like these other clouds that we see in our galaxy, and that these might be other galaxies, so other island universes away from our galaxy, so not located within our own galaxy. M51, looked pretty through a telescope for Lord Rosse. He was able to make this wonderful drawing. This is what it looks like through today's telescopes. So again, it's very obvious today that these galaxies are giant collections of stars that must be, comparable in size to our own galaxy. But back in the day, that was not obvious just by looking at the thing, although some people were of that opinion, that they must be other galaxies, other island universes. As I keep saying, it was sort of a matter of opinion because there were no direct measurements of how far away these galaxies were. So the first real hint that these galaxies must be outside of our own galaxy and therefore their own little universes came from Vesto Slipher. He was an astronomer working in the early 1900s, and he was the first person to take a spectrum of a galaxy and find that the spectrum of the galaxy was blue shifted. So he found a Doppler shift for the lines in the spectrum of a galaxy, and he found that they were shorter in wavelength than they were supposed to be, so that the galaxy, and he deduced that the galaxy is actually moving toward us at about 300 kilometers per second. Now, at this speed, you would be in Phoenix in less than a second. So this is moving really, really fast. Andromeda is essentially barreling towards us here in the Milky Way at 300 kilometers per second. And when he discovered this, he was essentially the only person in the whole world who knew that these faint, fuzzy, nebulous patches were actually moving in space at these very, very high speeds. He this seemed to indicate that if something was moving this fast, that it couldn't belong to our galaxy, because you don't expect things to be moving so much faster than everything else in the galaxy. But it wasn't until an actual distance measurement could be made, and this was made by Edwin Hubble in 1923. What he did was he again used a standard candle. He used these Cepheid variable stars, the same stars that Shapley had used for the globular cluster measurements, so those stars that were with the period luminosity relationship that was established by Henrietta Leavitt. And he was able to find Cepheid stars in Andromeda, so stars in another galaxy, and he was able to follow their brightness variations. And again, by measuring the period of those brightness variations, he can deduce how intrinsically luminous these stars are, and by knowing how intrinsically luminous they are and how bright they appear, he can estimate how far away they are. And so his estimate for the distance to Andromeda was 900,000 light years away, or 10 times further than the size of our own galaxy. So this was an underestimate because he got a few things wrong, but it still told us unequivocally that Andromeda was something that existed outside of our own galaxy, so was in fact its own little island universe. And this proved conclusively that our galaxy was not the universe, that there were other galaxies in the universe, and so that the universe was much, much larger than anyone had previously thought or measured. Hubble, as you'll see, went on to do a whole bunch of other really important discoveries, but all of these characters in the early 20th century were busy expanding our notion of the universe. The universe is quickly going to become bigger than anyone had previously thought. I'll leave you with this video that shows that basically takes you on a trip from Earth through the galaxy and beyond. So you might recognize in this first frame the stars of Orion. You'll see the Orion, the hunter with its 3 stars in the belt and the 3 stars in the sword, and through this flyby we're actually going to fly through the nebula in Orion, and then we're going to zip through the galaxy and then actually fly above the galaxy. And the really nice thing about this video is that this is a pretty realistic simulation, and that the position of the stars and the nebula and the relative positions of the galaxies that you'll see are all based on actual measurement. So let's go on this trip, and we'll see you next time.